Hello there, and welcome to Cosmic Lullaby. If you're someone who likes to unwind by thinking about stars, planets, and the quiet beauty of space, you're in the right place. Tonight, we're leaving our solar system behind and drifting into the darkness between the stars, where other planets orbit distant suns and almost anything is possible. We'll visit worlds that rain metal, planets made of ice and fire, and lonely giants drifting through space with no star at all. Some of what you're about to hear might sound impossible, and yet all of it is real. I'm Ray Nova, and this is Cosmic Lullaby, the place where we wander slowly through the wonders of the cosmos so you can rest. If you enjoy these sleepy journeys, you're welcome to like and subscribe. It helps others find their way here too. But for now, get comfortable, let your body rest, let your thoughts wander, and let's begin. There are planets with temperatures hotter than stars. Stars are known for their incredible heat, glowing plasma furnaces burning at millions of degrees. And yet, believe it or not, some planets come remarkably close. One such world, Kelt 9b, reaches temperatures above 7,000 degrees Fahrenheit, hotter than many red dwarf stars. This gas giant orbits so close to its massive blue sun that it completes a full circuit in a little more than a single day. The planet is tidally locked, with one side facing the star permanently, absorbing a relentless barrage of radiation. Its atmosphere is being torn apart, streaming out into space like the tail of a comet. The heat is so intense that molecules break apart and even metals can vaporize. It isn't just hot, it is extreme beyond comparison. These ultra-hot Jupiters challenge everything we once thought planets could be. They blur the boundary between planet and star, blazing storm-racked infernos that burn only briefly before dissolving into the darkness. And still, stranger worlds are waiting just ahead in our journey. Some planets might be made almost entirely of diamond. It sounds like science fiction, and yet, under the right conditions, it could be very real. Certain exoplanets, especially those rich in carbon, may form in ways that produce worlds composed largely of diamond. If a planet takes shape around a star that carries more carbon than oxygen, the ingredients present during its birth can give rise to carbon-rich structures. One candidate is 55 Cancri e, a super-Earth about twice the size of our own, which may hold an enormous amount of carbon locked beneath intense pressure. That pressure, deep within the planet's interior, could form vast regions of crystalline diamond. It wouldn't glitter or sparkle the way we imagine. There would be no jewelry here, only darkness, heat, and unimaginable density. Even so, the idea is captivating. A planet forged from carbon, a world where the mountains may shine with buried crystal, a place where geology becomes something almost otherworldly and precious. Some exoplanets orbit two suns, much like Tatooine in Star Wars. In science fiction, we've long imagined twin sunsets, two stars slowly sinking beneath a distant horizon. And now we know that those strange skies might actually exist. Certain exoplanets do not orbit a single star the way Earth does. They orbit two. These are called circumbinary planets, and they move in beautiful, complex loops around pairs of suns that circle one another. When the two stars sit close together, a planet can travel around them both as if they were a single body. But when the stars are farther apart, the planet may orbit only one of them, gently tugged and tilted by the distant pull of the other. The result is a world with unusual light cycles, changing seasons, and double shadows that stretch across the ground. These systems are rare and delicate, yet they do exist. So the sky of some distant world may truly glow with two dawns and two dusks. A sky once imagined only in fiction and now quietly confirmed by science. There are planets where it rains molten glass. Some worlds are so alien that even their weather defies the imagination. Consider HD 189733b, a gas giant larger than Jupiter, orbiting so close to its star that it completes a full circuit in a little more than 2 days. The planet's atmosphere is scorching, with temperatures near 1,700 degrees Fahrenheit. Winds race around it at thousands of miles per hour, and suspended in its blue, hazy skies drift tiny particles of silicate, the very building blocks of glass. When the conditions are right, these particles condense and fall as rain. Not water, not ice, but molten glass, swept sideways by high-speed winds. From far away, this planet looks strangely Earth-like in color, a soft blue shimmer glowing near its sun. Yet up close, it is a storm furnace, beautiful, violent, and utterly uninhabitable. It is one of many exoplanets that remind us how nature's imagination reaches far beyond our own. And still stranger worlds lie waiting in the quiet. Others may be covered in oceans thousands of miles deep. Some exoplanets might be ocean worlds, planets almost entirely wrapped in water. No continents, no islands, only endless global seas. These are not like Earth's oceans, which reach only a few miles down. On these worlds, the water layer could stretch hundreds or even thousands of miles thick. At the surface, it might be calm, wind-borne, or stormy. But deep below, the pressure would climb to incredible extremes, giving rise to exotic forms of ice. Not the kind we know, but dense, high-pressure ice that forms only under crushing weight. These planets may hold rocky cores at their centers, hidden far beneath the water. Some may even have liquid layers, warmed by the planet's own internal heat. Could life exist in such oceans? We do not yet know. But ocean worlds may be more common than we once thought. Gentle, glistening planets with no land in sight, quietly turning in the dark, far from any sun we know. Some planets are tidally locked, so one side always faces the star. Not every world spins the way Earth does. Some are tidally locked, meaning that one side of the planet forever faces its star, while the other remains in permanent darkness. The same is true of our own moon, of which we only ever see a single side. Now imagine that on a planetary scale. One hemisphere scorched by unending daylight, while the other is trapped in eternal night. And between them lies a twilight zone, a ring around the planet where the light is always low and where the temperature might just be right. Some scientists believe that in certain cases, life could survive within this thin band of balance. These worlds may be swept by fierce winds, wrapped in strange cloud formations, and shaken by wild extremes of weather. Yet they are real, and they challenge our ideas of what makes a world habitable. Life, if it exists, might learn to thrive in the shadows or just along the edge of the light. Let your breath slow and let your thoughts drift a little further from the day. Hot Jupiters skim so close to their stars that their atmospheres are quietly boiling away. Imagine a planet like Jupiter, massive, gaseous, immense. Now move it far closer to its star, so close that a single orbit takes only days, so close that temperatures climb beyond 2,000 degrees. These are the hot Jupiters, giant worlds that graze just above their stars' surfaces, so near that their upper atmospheres are literally being blown away into space. We have discovered many of these strange worlds, often among the very first exoplanets we ever detected. Their sheer size and their tight orbits make them easier to spot, and yet they remain deeply mysterious. How did such massive planets end up so close to their stars? Did they form there, in that inferno, or were they pushed inward over time by gravitational forces? Some trail glowing tails of gas like comets. Others are slowly shrinking as their atmospheres evaporate into the dark. They are unstable, dramatic, and often short-lived. Brief flashes of planetary fire, circling faraway suns. And yet, before you slip too far into rest, the strangest sights are still ahead. Some exoplanets are darker than charcoal, Not every world reflects light the way Earth does. Some absorb almost everything that touches them, becoming darker than paint, darker than ash, darker even than charcoal. One such world is TRES 2b, a gas giant orbiting a star roughly 700 light-years away. Its atmosphere reflects less than 1% of the light that strikes it. Scientists are not entirely sure why. It may be due to vaporized alkali metals, or to unknown chemical compounds drifting in its upper layers. Whatever the cause, the result is extraordinary. A planet as dark as coal, glowing faintly with its own heat, nearly invisible in reflected starlight. Even its night side, already sunk in darkness, is only slightly cooler than the day. If you could stand nearby and look toward it, you might see only the faintest silhouette against the fire of its star. A nearly perfect shadow, orbiting in silence, drinking in the light of the universe. Let that image settle softly behind your eyes, a dark sphere adrift against the glow. We have found planets floating alone, without a star of their own. Most planets orbit stars, but not all. Some are wanderers, free-floating worlds that drift through space alone, unbound by any sun. These are known as rogue planets, and we have found evidence of dozens, perhaps hundreds, scattered across the galaxy. They may have formed normally, then been cast out of their home systems by gravitational disruptions, or they may have formed in isolation, like failed stars that never gathered enough mass to ignite. These worlds are dark, cold, and remarkably difficult to detect, but with powerful infrared telescopes, we can catch hints of their faint thermal glow. Some may still hold internal heat, keeping subsurface oceans warm for billions of years. Others may be completely frozen, drifting forever through the black. A planet without a sunrise, a world with no sky. And yet, even here, the quiet question lingers. Could something live in such deep stillness? Some worlds may wear clouds of ruby and sapphire. When we think of clouds, we picture water vapor, soft, pale, ever-shifting. But on some exoplanets, the skies may shimmer with gems. On scorching hot gas giants, where temperatures soar above 2,000 degrees, minerals that would be solid rock on Earth can vaporize, rise into the atmosphere, and then condense into clouds. Aluminum oxide, iron, titanium, and in some cases corundum, the mineral form of rubies and sapphires. These mineral clouds may scatter light in strange ways, tinting entire skies red, purple, or deep, endless blue. On one such planet, HATP 7b, researchers have watched shifting patterns in the atmosphere that suggest high-altitude mineral clouds sweeping across the sky. It is hard to picture a world wrapped in heat and storms, lit by a blazing sun, with clouds of liquid gems glinting and swirling overhead. The universe is stranger and more beautiful than we can easily imagine. Breathe slowly and let that beauty carry you a little deeper. There are super-Earths that could be more habitable than Earth itself. Some exoplanets fall into a category called super-Earths, rocky worlds larger than our own, but smaller than Neptune. They may have stronger gravity, thicker atmospheres, and more stable climates, and some of them may be even more hospitable to life than the planet beneath us. One such candidate is Kepler 442b, a rocky world in the habitable zone of its star. Not too hot, not too cold. It receives just the right measure of sunlight, and it seems to have the mass needed to hold on to an atmosphere and perhaps liquid water. Some super-Earths could have deeper oceans, fewer tectonic disruptions, and greater surface stability, all conditions that might help life emerge and endure. We do not yet know if any of these worlds are truly habitable, but they whisper something humbling to us. Earth may not be the perfect planet, only the one we happen to call home. We have seen planets that complete an orbit in just a few hours. Most planets take months or years to circle their star. Earth takes 1 year. Mercury, the fastest planet in our solar system, takes 88 days. But some exoplanets move much faster. We have found worlds that orbit their stars in a matter of hours. One of the swiftest is Kepler 78b, a planet only slightly larger than Earth, which completes a full orbit every 8.5 hours. It rides so close to its star that its surface is likely drowned in molten rock. Temperatures climb into the several thousands of degrees. These ultra-short period planets are often tidally locked, their days and nights frozen in place. Their stars loom huge across the sky. Gravity tugs at their very structure, and some may be slowly tearing themselves apart. These planets are extreme, fast, hot, and fleeting, yet they exist, skimming the edges of their stars like sparks flying from a flame. And still the sky holds a gentler rhythm as well. Other planets take centuries to complete a single orbit. While some exoplanets race around their stars in mere hours, others take their time, drifting in long, patient loops through the dark, as if unwilling to hurry through the night. Long, silent journeys that can last for centuries. One of the slowest moving planets we have found is Gu Piscium b, a gas giant that takes about 1,000 years to complete a single orbit around its star. Its path is so distant, so far removed from the warmth at the center, that gravity barely holds it in place. If it drifted any farther, it might slip free entirely and wander off into the dark forever. These long-period planets are incredibly difficult to detect. We cannot wait 1,000 years to watch one of them close its loop. Instead, we catch them in motion, in a single fleeting glimpse, a curved path, a long arc, a hint of something vast passing quietly through the night. Some of these planets may have cold, dark surfaces, illuminated only faintly by starlight, as though lit by a candle held at the far end of a great hall. Others may experience seasons that last entire lifetimes. On such worlds, change is measured not in years, but in generations, a slow and silent rhythm far beyond our own sense of time. Let your breath soften now, and let your thoughts drift with that rhythm, gently, without hurry. And as you rest there, imagine this. We have already discovered thousands of planets beyond our solar system, and yet the strangest part of the story is still ahead. For most of human history, we only knew of one planetary system, our own, the sun, the moon, and the wandering stars that moved slowly through the night sky. That was all the universe seemed to offer. But everything changed in the 1990s, when the first exoplanets were finally confirmed. A quiet revolution, unfolding in the calm hush of observatories and printed pages. Now, thanks to space telescopes like Kepler and TESS, we have found thousands of planets circling distant suns, some small, rocky, and Earth-like, others massive and strange beyond easy words. Some orbit tightly, completing a year in just a few days. Others take centuries to trace a single loop around their star. Each discovery reshapes what we once thought was possible. And still, this is only the beginning. We now believe there are hundreds of billions of planets in our galaxy alone, more planets than stars, worlds upon worlds, quietly turning in the dark, most of them unseen, unnamed, and unvisited. We will never reach the vast majority of them, but we can listen for them. We can measure their shadows. We can wonder, softly, what else might be waiting out there beyond the reach of our small blue home. Some of these planets we have detected through the shadows they cast during transits. The light from a star is usually steady, patient, unchanging over long stretches of time. But sometimes, just briefly, it dims. A tiny dip, a momentary flicker. That subtle darkening can mean that a planet has passed in front of it. This is called the transit method, and it is one of the most powerful tools we have for finding exoplanets. When a planet crosses in front of its star from our point of view, it casts a faint shadow. Not in the dramatic way we see with eclipses here at home, but in gentle drops in brightness, often less than 1%. Space telescopes like Kepler and TESS have used this technique to uncover thousands of exoplanets. From just those shadows, we can learn a planet's size, its orbit, and even hints about its atmosphere. We are watching stars blink, ever so slightly, in order to learn about worlds we have never seen. The light of a distant sun, interrupted by the quiet silhouette of a planet drifting far away. Others were found not by their shadow, but by the gravitational wobble they induce. Even a planet's gravity can leave a fingerprint on its star. When a planet orbits, it does not simply travel around the star. It also causes the star itself to move, ever so slightly. This wobble is tiny, but it is real. As the star shifts back and forth, its light shifts with it, gently squeezed and stretched by that unseen motion. Astronomers can detect those changes using spectroscopy, breaking starlight into its many components and looking for the subtle signatures of movement. This is called the radial velocity method, and it was the way in which the first exoplanets were discovered. It works best for massive planets close to their stars, like hot Jupiters, but it has also helped us find multi-planet systems and long-period orbits. We are not seeing these planets directly. We are watching their stars sway under an invisible pull, like a dance too distant to see, but close enough to feel in the quiet music of the light. Some exoplanets appear to have atmospheres slowly escaping into space. A planet's atmosphere is never truly still. Winds blow, clouds drift, particles rise and slip away. But in some extreme cases, the entire upper atmosphere may be drifting off, leaking into space like a long exhale into the void. This is especially common in hot, close-in gas giants, where intense radiation from the nearby star heats the outer layers until they reach escape velocity. These planets can develop long, comet-like tails of escaping hydrogen and helium. We have seen this in several exoplanets, where ultraviolet light reveals trails of gas streaming behind them, soft banners drawn across the dark. Some planets may lose significant mass this way over time. Others might be stripped down to nothing more than rocky cores. This process helps shape the evolution of entire planetary systems, showing us how stars can sculpt, reshape, or even destroy their planets. It is a quiet reminder that even worlds can change, erode, and fade, leaving only their gravity behind. We have also found planets in star systems with 3 or more suns. Not every star system is like ours. Some contain not 1, but 2 or 3 or even more stars orbiting together in slow, intricate patterns. And in a few of these tangled systems, we have found planets. Imagine for a moment a world where the sky is never truly dark, where shadows stretch in different directions at once, where one sun rises while another quietly sets on the far horizon. These planets must follow delicate, stable paths to survive the tangled pull of so many stars. Some orbit closely around a pair of stars, circumbinary planets, echoing the twin sun skies of imagination, with double shadows drifting across their surfaces and seasons that shift in ways we can barely picture. Others orbit far beyond the entire cluster, tracing wide loops around a chaotic center of light. The illumination on such worlds would be strange, the seasons unpredictable, the sky full of gentle, constant motion. And yet these planets exist. They remind us that planetary systems can form in ways we never expected, even in places where gravity is complicated and the night sky never quite settles. Planets somehow find a way, and still more astonishing worlds await. Some planets orbit the collapsed remains of stars that have already died. Stars do not live forever. Some end their long lives as white dwarfs, small, dense remnants of of stars once like our own sun. Others collapse into neutron stars, or even black holes, sinking into silence at the end of their fire. And around some of these stellar corpses, against all expectation, we have found planets. These worlds orbit what remains after a star has died. Glowing embers or pulsing remnants of stellar fury, still turning quietly in the dark. In some cases, they are survivors, somehow enduring the chaos of a supernova. In others, they may have formed from the debris left behind, rising from ashes into something new. The light from these stars is dim, cold, or distorted, a strange lantern held above worlds that have already outlived their sun. And still, the planets remain, tracing silent paths through a kind of stellar graveyard. Some are scorched by radiation, others drift quietly, circling dead suns in an eternal twilight. It is haunting and beautiful, a soft reminder that even after the end, something new and strange may begin again. Let your breath slow as you drift with them, through these dim corridors of light and memory. Now imagine a world that orbits its star backwards. Most planets move in the same direction their star spins. That is how solar systems usually take shape, from a single swirling disk of gas and dust, all turning together in one calm choreography. But nature does not always follow the rules. We have found at least one exoplanet, WASP-17b, that circles its star in the opposite direction. Instead of drifting along with the star's rotation, it pushes gently against it, like a swimmer moving against a slow current. This backwards orbit likely formed through chaos long ago, a near collision, a gravitational shove, or some violent rearrangement in the distant past. The planet itself is massive, bloated, and blisteringly hot, sweeping close to its star every few days. The fact that it moves in reverse quietly challenges our understanding of how planetary systems evolve, and it whispers something important. The universe is more flexible, more chaotic, and more surprising than any single theory can hold. Some worlds follow the flow, others push against it, and some, like this one, move through the cosmos with a soft, patient defiance. Let your thoughts wander farther still, because we have even seen signs of clouds on planets light years away. It may seem impossible, but we have detected traces of clouds on exoplanets dozens, even hundreds of light years distant, not by seeing them directly, but by studying the way starlight passes through a planet's atmosphere during transit. As the light filters through the thin edge of an alien world, some wavelengths are absorbed, while others pass through or scatter. And this delicate fingerprint tells us about the gases, molecules, and particles suspended in the air. In several cases, the data suggests the presence of clouds, not white, cottony clouds like those drifting over Earth, but dark, metallic, or mineral-based veils, made from silicates, iron, or exotic chemicals. These clouds might reflect or block starlight, gently shaping a planet's appearance and temperature. Some worlds are permanently cloud-covered, wrapped in a slow, uniform hush. Others show changing patterns across their skies, weather systems shifting in silence. We cannot yet see these worlds up close, but we can read their weather from starlight alone. And here is a thought worth sitting with as you drift towards sleep. Some exoplanets orbit closer to their stars than Mercury does. Mercury is already scorching, the closest planet to our sun, bathed in light and stripped of atmosphere. But some exoplanets travel much nearer to their stars, at distances where no world in our solar system could survive. These worlds complete a full orbit in mere hours or days. Their surfaces may be molten. Their atmospheres are whipped away by relentless stellar winds. Some are tidally locked, one side blistering in unending daylight, the other frozen in eternal night. Others move so close that they bulge from tidal forces, stretched into the soft shape of a teardrop by their star's gravity. These extreme worlds challenge our ideas of habitability, and yet they are among the easiest to detect, thanks to their short orbital periods. Many of the very first exoplanets discovered belong to this family. They are hot, hot and often unstable, but they show us just how flexible and extreme planetary systems can be. And then, at the other end of the story, there are worlds that drift far beyond the reach of any sunlight. Not all planets huddle close to their stars. Some orbit so far away that sunlight becomes a faint and feeble glow, barely more than a distant candle. These remote worlds may take hundreds, even thousands of years to complete a single orbit. Temperatures plummet into unimaginable depths. Seasons span generations, unfolding across the lifetimes of countless beings. And in the deepest cold, chemical reactions may slow to the softest crawl. Yet even here, planets persist, silent and slow, circling their stars at the very edges of gravity's reach. Some may be icy giants, wrapped in frozen clouds. Others could be rocky and barren, crusted over with ice and carbon dust. And some may hide warmth beneath their surfaces, sustained by radioactive decay or ancient heat trapped from the moment of their formation. These far-flung orbits are hard to detect, but their existence gently reminds us that planets can survive in places we once believed were empty. Even in the loneliest reaches of space, a world can quietly endure. Now picture this, because the strangest sight may still lie ahead. There are planets thought to carry spectacular ring systems, so vast they defy imagination. Saturn's rings are beautiful, delicate bands of ice and dust, suspended around a gas giant, a familiar wonder in our own sky. But they may not be the most impressive rings in the universe. Some exoplanets appear to have rings thousands of times larger, stretching across vast distances, wide enough to eclipse their host stars entirely. One candidate is J1407b, a giant planet or brown dwarf that may be surrounded by a ring system more than 200 times larger than Saturn's. These rings could be made of ice, rock, or dust, possibly the remnants of forming moons. As the planet moves along its orbit, its rings may cast deep shadows on the star, creating strange dips in light that we can detect from Earth. If such a world were placed in our solar system, its rings would stretch across the entire night sky, a slow, majestic arc from horizon to horizon. They remain hypothetical for now, but their shadowy presence hints at the grandeur still waiting to be confirmed. Let this thought settle softly in your mind. We have only just begun to scratch the surface. For all that we have learned about exoplanets, we are still at the very beginning of this journey. The first confirmed discovery was made in the year 1992. In cosmic terms, that is barely a heartbeat ago. Since then, technology has leapt forward. Thousands of planets have been found, and thousands more await confirmation. We have detected atmospheres, measured sizes and orbits, and mapped their skies in light and shadow. But we have barely begun to understand what these worlds are truly like. We cannot yet see their surfaces. We do not know what they smell like, sound like, or feel like beneath imagined footsteps. We cannot yet say which ones carry clouds, continents, or living things. The truth is, every new exoplanet we discover is a doorway to something we have never seen before. And as our tools grow sharper, the picture will only grow stranger, richer, and more full of wonder. The cosmos is full of worlds, and we have only just knocked, gently, on the door. And somewhere out there, some planets orbit so close to their stars that they are slowly being vaporized. For some exoplanets, being close to a star means far more than simply being hot. It means slow destruction. These worlds orbit so near their suns that the searing radiation and relentless stellar winds begin to peel them apart, layer by layer. The outer edges of their atmospheres heat up, expand, and drift away into space. Some trail long, glowing streams of gas behind them, like comets caught in an endless, quiet retreat. Over time, these planets lose mass, gradually shrinking, thinning, or transforming into something else entirely. One such world, known as KIC 12,557,548b, may be slowly crumbling under this kind of erosion, shedding dust and debris with every orbit. It is a little like watching a planet dissolve in slow motion, a fading silhouette against the light. These are not simply places to live. They are living systems, constantly reshaped by their surroundings. Even something as vast as a planet can be worn away, little by the unrelenting glow of a star. Let your thoughts drift for a moment, because the deeper we look, the stranger it all becomes. We have discovered worlds that defy every expectation. Each time we believe we finally understand what a planet can be, the universe hands us something we cannot quite explain. We have found worlds where the skies shimmer with vaporized metal. We have found rocky planets hotter than lava, and giant gas planets colder than the deep of space. We have seen worlds with tilted orbits, backward spins, and rings so wide they could nearly blot out a star. Some planets are impossibly dense, others are startlingly light. A few should not exist at all, at least not according to our models. And yet, quietly, they do. Each strange discovery gently forces us to rethink how planets form, how they evolve, and what might still be possible out there in the dark. Science thrives on these surprises. In the chaos of the cosmos, order is only part of the story. The rest is made of exceptions, edge cases, and quiet contradictions, small cosmic puzzles scattered through space, waiting for someone to notice them and wonder. Now let your breath slow and picture this. Some exoplanets may be water worlds with no land at all. Imagine a planet with no continents, no islands, no shorelines, only endless oceans stretching in every direction. These are the water worlds, exoplanets where the surface may be entirely covered by liquid water, not shallow seas like Earth's, but oceans hundreds, even thousands of miles deep. Beneath the surface, the pressure would be immense, enough to compress water into exotic, high-pressure ices, and to crush rock into shapes unfamiliar to anything on Earth. Some of these worlds might carry atmospheres rich with steam, or drift beneath slow clouds of vapor. Others could be wrapped in soft, hazy mists, warmed either by distant sunlight or by heat rising from within. If life exists on such planets, it would evolve in a deep, sunless sea, shaped by currents and chemistry rather than by light. We have not confirmed one yet, but the evidence is quietly growing. And if Earth is one kind of habitable world, then perhaps these dark oceans are another kind entirely, still hidden, still waiting to be understood. Between the familiar and the strange lie many more worlds, small but swollen with gas. Not every exoplanet falls neatly into the categories we already know. Between Earth and Neptune sits a curious family of worlds called mini-Neptunes. They are larger than Earth, yet smaller than our ice giants, and many are wrapped in thick, muffling layers of gas. These planets likely hold rocky or icy cores, surrounded by envelopes of hydrogen, helium, and other gases. From a distance, they might look a little like Neptune itself, but inside they could be wildly different. Some may hide deep, boiling oceans beneath their clouds. Others might have no solid surface at all. They are too small to be true gas giants, yet too large to be rocky super-Earths. For a long time, we did not even know if planets like this could exist. Now we know they are common, possibly the most common type of planet in the galaxy. Strange, swollen, and still full of mystery, they fill the quiet gap between what we expected and what we found. And there is stranger still ahead. Some planets are puffed up like balloons, drifting on the edge of belief. Certain exoplanets are so inflated, they seem lighter than they have any right to be. These puffy planets are enormous in size, yet yet remarkably low in density. Huge, soft worlds that could, in theory, float in water, if only there were a bathtub somewhere the size of a star. One well-known example is WASP-17b, a gas giant nearly twice the size of Jupiter, but carrying only a small fraction of its mass. These planets likely formed far from their stars, then slowly migrated inward. Now the intense heat of their sun causes their atmospheres to swell and expand outward. Radiation from the star may also be breaking apart the molecules in their air, adding to their strange, delicate properties. Some puffy planets even trail visible tails of escaping gas. Others simply seem impossibly light for their size. We still do not fully understand them, but they gently remind us how elastic a planet can be, not rigid and fixed, but soft, unsettled, and stretched by the pressure of light. Let your thoughts wander a little further, because there are exoplanets where a single day is longer than an entire year. On Earth, a day and a year are very different things. We spin on our axis once every 24 hours, yet it takes 365 days for us to complete a single orbit around the Sun. That balance is not shared by every world. On some exoplanets, especially those hugging close to their stars, the time it takes to rotate is longer than complete an orbit. In other words, the planet finishes a full loop around its star before it has even turned once on its own axis. These worlds are usually tidally locked, with one side facing their sun forever. The night side remains in darkness, frozen and still, while the day side burns endlessly under a sun that never moves. There is no sunrise, no sunset, only one eternal face turned toward the light. On such a world, the very idea of time begins to soften and blur. A day that never ends, a year that races by, a sky divided, quietly and permanently, in two. And finally, before we drift onward, imagine worlds veiled in thick, hazy skies. We often picture alien planets with clear air and breathtaking views, but some exoplanets may be wrapped in dense layers of haze, blocking the light and hiding everything below. These hazes can be woven from complex hydrocarbons, from photochemical smog, or from exotic clouds shaped by chemistry we barely recognize. On Earth, we glimpse this kind of effect on Saturn's moon Titan, where a soft golden fog hides the surface entirely from view, leaving only quiet color and light above. On exoplanets, especially those drifting around cooler stars, ultraviolet light can trigger strange, slow reactions high in the upper atmosphere, building up thick, murky layers that trap heat and scatter light into soft, uncertain shades. These worlds may look dull or muted from space, their colors softened by that hanging veil of haze. Yet beneath the clouds, oceans might churn in silence, winds might scream across unseen plains, and alien landscapes may wait quietly for a light that never truly reaches them. We cannot see them clearly, not yet, but we know the haze is there, a gentle curtain drawn over distant, hidden worlds. And the strangest part is that it is only the first of many veils we are about to lift together. Rest for a moment now, and let your breath slow, because our journey moves on to something even more astonishing. On many exoplanets, we have found signs of winds whipping through their skies at thousands of miles per hour. Weather, it turns out, does not only happen on Earth. Across countless distant worlds, especially the great gas giants, atmospheric winds can reach extraordinary speeds, far beyond anything we know from our own quiet corner of the solar system. Some of these exoplanets are tidally locked, with one hemisphere forever facing their star, while the other is trapped in endless night. That intense, unrelenting heat creates powerful thermal gradients, and those gradients drive fierce, sweeping winds that circle the planet without pause. Using space telescopes, astronomers have detected signs of winds racing at up to 50,000 miles per hour, fast enough to cross the width of the United States in less than a single hour. Let your thoughts wander with those winds for a while. Feel how they shift entire cloud decks, reshape hidden heat patterns, and carry vaporized metals across whole worlds. Some of them even seem to redistribute light itself, gently nudging the brightest point of the planet away from where its star pours down most directly. It is invisible to the eye, but written softly into the glow of the planet's own light, a whisper of motion in a faraway sky. Now imagine, as you drift a little deeper, that a planet could be quietly heated from within, needing no sunlight at all. Not all warmth in the universe comes from a star. Some exoplanets, especially those on eccentric oval orbits, may be heated from the inside out by the pull of tidal forces. As they move through varying gravitational fields, their interiors stretch and flex, and that endless flexing creates friction and warmth deep beneath the surface. This is how Jupiter's little moon Io stays volcanically alive, and exoplanets can experience the very same thing. Worlds orbiting close to large stars, or caught in gravitational dances with neighboring planets, can be kneaded by these tidal forces. In some cases, that hidden heat could melt rock into rivers of magma, or keep vast subsurface oceans liquid beneath thick shells of ice. From the outside, these planets might look cold, dark, almost forgotten, yet inside they are alive with quiet motion. Heat without sunlight, activity without a star. It is a soft reminder that energy can come from within, and that even in the far outer reaches of a distant system, a planet may still be gently warm. Breathe in slowly, breathe out slowly, and let yourself drift even further back through time, because we have also discovered planets in ancient star systems, so old they almost predate the very idea of worlds. Some stars are nearly as old as the universe itself, formed in the galaxy's earliest chapters, when everything was still young and unfamiliar. And around a few of these ancient stars, we have found planets, quietly orbiting for billions of years, far longer than Earth has existed. One example is a star system known as Kepler 444, believed to be more than 11 billion years old, with 5 small, rocky planets circling it in patient rhythm. These worlds come from a time when the universe held far fewer heavy elements, suggesting they may have formed from very different materials than our own Earth. What might such planets be like? Could they be worn smooth by eons of impacts, their surfaces polished by countless slow collisions? Could they have once supported life, long before life ever began here? We may never know, but these ancient systems remind us how long planets can last, surviving stellar storms, galactic tides, and the slow, unhurried march of time. They are cosmic elders, quietly circling in the deep past, still here, still turning. And as you settle a little more comfortably into that thought, know that some exoplanets may have moons we have yet to find. Where there are planets, there may also be moons. And yet, for all the exoplanets we have discovered so far, exomoons, moons orbiting planets outside our own solar system, remain elusive. They are hard to detect, small, subtle, often hidden in the noise of the stars. But we have seen hints. Tiny variations in a planet's transit, faint wobbles in timing, gentle dips in brightness that do not quite match the model. One candidate, a possible moon orbiting the gas giant Kepler 1625b, is still being studied. If it is ever confirmed, it would be enormous, larger than any moon in our own solar system. But even smaller exomoons could be deeply important. They might stabilize planetary climates, shape tides, or even provide sheltered environments where life could quietly take hold. Some moons could hide subsurface oceans, like Europa or Enceladus. Others might be rocky and cratered, drifting in twilight above enormous gas giants. We have not seen them clearly yet, but they are almost certainly out there, circling in the quiet, waiting to be found. And some worlds, others still, could have entire moon systems of their own. Just as planets orbit stars, moons orbit planets. And for massive exoplanets, especially towering gas giants, it is very likely that they carry whole systems of moons with them. In our own solar system, Jupiter and Saturn each have more than 80 moons, ranging from tiny captured asteroids to massive worlds with hidden subsurface oceans. Now imagine, softly, a gas giant many times more massive than Jupiter, drifting around a distant star. It could hold dozens, perhaps hundreds of moons, a miniature solar system all its own. Some of those moons might be rocky and cratered, scarred by ancient impacts. Others could wear icy shells or thick, swirling atmospheres. A few might even orbit within the habitable zone of their parent planet, sheltered from harsh stellar radiation and gently warmed by tidal forces. We have not confirmed any of these exomoon systems yet, but the potential is quietly staggering. Not just planets, but whole families of worlds drifting together, locked in gravitational harmony, far from home. And here, as your breathing grows softer, comes perhaps the most tender thought of all. Some exoplanets might support life, but not as we know it. When we imagine alien life, we often picture Earth-like conditions, blue skies, liquid water, and a comfortable range of temperatures. But life may not need any of those things. Some exoplanets could host life in environments wildly different from our own, in acidic clouds, beneath ice-covered oceans, or within high-pressure atmospheres thick with methane. There could even be life that does not rely on water, or carbon, or DNA at all. Extremophiles on Earth already survive in boiling acid pools, radioactive caves, and near volcanic vents where no sunlight ever reaches. So on distant planets, it is entirely possible that life could take stranger, quieter forms. Not walking, talking creatures, but microbial networks, delicate chemical colonies, or self-replicating systems that thrive in environments we would find utterly deadly. We may never meet them, but if you listen closely, in the light and shadow of alien worlds, we might one day catch the first faint signature, a chemical imbalance, a breath of something living, drifting across the void. We have found planets that barely skim the edge of being stars. There is a line between planet and star, and some exoplanets sit right at that threshold. These enormous objects are called brown dwarfs, or superjupiters. They carry enough mass to fuse a little deuterium in their cores, but not enough to sustain the fusion reactions that power true stars. They glow faintly with leftover heat from their formation, and some may even give off a soft breath of infrared radiation. One such object, called HD 142546b, is so large and so hot that it may straddle the boundary between planet and failed star. Scientists are still debating where the cutoff truly lies. How massive can a planet grow before it becomes something else entirely? These in-between worlds may form like planets or like stars. We do not always know which, but they remind us that categories in space are often blurry. The cosmos is full of edges that shimmer and shift, where one thing slowly becomes another. Let your breath settle for a moment and drift with that thought, because the strangest boundaries are still ahead. Some worlds lie right on the edge of the habitable zone. That zone is often called the Goldilocks zone, the gentle ring around a star where temperatures are just right for liquid water. But many exoplanets rest on the very rim of this zone, where conditions grow more uncertain. Drift too far out, and water freezes into stone. Drift too close in, and it boils away into vapor. On the boundary, things become far more complex. A thick atmosphere might trap heat like a warm blanket. A high reflectivity might keep a planet cool, bouncing starlight back into space. Seasonal shifts or a stretched, eccentric orbit could cause dramatic climate swings. One hemisphere might be habitable, while the other remains too cold or too hot to bear. Life could exist only in quiet pockets, beneath sheets of ice, in the hush of deep caves, or gathered around the warm mouths of volcanic vents. These edge worlds are neither fully comfortable nor completely barren. They are places of tension and possibility, where the balance between warmth and cold, light and dark, could tip either way, or hold, just barely, for ages. We are slowly learning to read the chemistry of alien atmospheres. Until recently, the very idea of studying the air of a planet many light years away seemed impossible. But now, thanks to precise instruments like the James Webb Space Telescope, we are beginning to do exactly that. When an exoplanet passes in front of its star, a thin thread of starlight filters through the planet's atmosphere on its way to us. That light carries subtle fingerprints, spectral lines drawn by the molecules floating in the air. By breaking that light apart and studying those delicate lines, scientists can detect water vapor, carbon dioxide, methane, and more. They can begin to guess at clouds, at pressure, even at temperature. In some cases, they may even glimpse biosignatures, chemical hints that life itself might be shaping the atmosphere. It is like reading a message from across the galaxy, hidden inside the colors of starlight. We are still very early in this work, yet with each new spectrum, we drift a little closer to understanding what alien skies are truly made of. Some exoplanets may have seasons that last for decades. Here on Earth, our seasons are shaped by a gentle tilt, a soft lean that changes the angle of sunlight across the year. But on some exoplanets, the mechanics are far more extreme. A steeper tilt, a stretched orbit, or a family of multiple stars can create wild seasonal effects, with summers that stretch on for decades and winters that span entire lifetimes. A planet might swing close to its star, warming dramatically in a slow golden bloom, then drift away into a deep frozen hibernation. Others might have chaotic seasons, shifting unpredictably with every orbit. Long summers could allow life to flourish, only to vanish beneath decades of cold. Or entire generations might live and die within a single long spring. The rhythm of life on such a world, if it exists at all, would follow a different kind of calendar, written not in days or years, but in slow arcs and stellar dances. On these worlds, time moves differently, and perhaps everything else does too. Others might drift through eternal twilight. Some exoplanets may live forever in the in-between, a place where day never fully breaks and night never fully falls. This can happen on tidally locked planets, where one side always faces the star and the other side never does. Between these extremes lies a thin region called the terminator, a ring of perpetual twilight. Here the sky might glow dimly, forever, caught between burning light and endless dark. Temperatures could be more stable, winds more gentle and moderate. If life exists there, it might flourish along this twilight boundary, a narrow band of soft shadows and muted warmth. There would be no sunrise, no sunset, only the slow, slanted glow of a star locked at the edge of the sky. A planet with a horizon that never moves, a place where time drifts in half-light and nothing ever truly sleeps. We have also discovered planets locked in orbital resonance with one another. In some star systems, planets do not simply orbit alone. They move together in quiet synchrony. These arrangements are called orbital resonances, where the timing of their orbits aligns in whole number ratios. For every 2 orbits one planet makes, another completes exactly 3. This balance keeps them from colliding and helps steady their motion through the ages. We see this in our own solar system, among Jupiter's moons, for example. But we have also found exoplanetary systems with long chains of resonance involving 3, 4, or even more planets. It is like a cosmic symphony, with each world playing its own gentle rhythm, separate, yet always in harmony. These arrangements are delicate. A small change in gravity or in motion could throw everything off, and yet they hold, gently, beautifully, orbit after orbit after orbit. The universe, it seems, is not only chaotic, it is also deeply musical. Some planets carry mysterious signals we still do not fully understand. Not everything we observe makes sense right away. Some exoplanets show light curves that flutter unexpectedly, dimming and brightening in ways that do not match any simple model. And the strangest part of that puzzle is still waiting, softly, a little further along. Others appear to wear rings, or drifting clouds, or orbiting debris that cast irregular shadows across their faces. One star, gently nicknamed Tabby's star, dimmed in strange, uneven patterns that stirred a quiet wave of curiosity across the world. Some thought it might be a passing swarm of comets. Others imagined vast artificial structures, though no evidence supports that idea. Still, the mystery lingers, soft and unresolved. Light curves wiggle and wobble. Transit patterns shift ever so gently. Some planets show extra dips in brightness before or after they pass in front of their stars. Others seem to change shape, as if wrapped in clouds or trailing veils of dust. We are only beginning to decode these patterns. For now, they remain unanswered questions, gentle flickers of something we do not yet understand, but somehow cannot look away from. And there is more still to come, because just ahead lie worlds whose orbits are wilder than any story you have heard so far. There are planets with orbits so wild they nearly escape their stars. Most planets move in quiet, regular loops, patient and steady, but some exoplanets follow long, stretched-out paths, so elongated that they swing far away from their stars before plunging back in like cosmic comets. These orbits can last hundreds of years. At their farthest point, the planet may receive almost no light, almost no warmth. At their closest, they race past their star, pulled in by intense gravity, heated in brief, blinding flashes. These journeys are violent, unstable, and often only temporary. Some planets may have been flung into these orbits by ancient collisions or by the passing tug of another star. Others may one day be lost entirely, drifting free of their systems into interstellar space. They are cosmic exiles, barely bound, dancing on the very edge of gravity's grip. Their paths are unpredictable, their futures uncertain, and yet, still, they orbit. Each pass a soft reminder of how dynamic and dramatic the life of a planet can be. Let your breath slow again, because our journey now drifts towards stranger companions still, worlds that orbit the burnt-out corpses of stars. After a star like our sun completes its long life, it leaves behind a white dwarf, a small, dense ember of what it once was. These stars no longer fuse hydrogen. They do not shine with the fierce energy of youth, yet they remain hot and softly bright for billions of years. And around some of these stellar remnants, we have found planets. Some hover close in, having somehow survived unimaginable changes as their star ballooned into a red giant and then collapsed. Others may have formed later, gathered from the leftover debris. The environment is extreme. Radiation can be intense. The gravity near a white dwarf is crushing, and yet, even here, planets persist. Some may even lie within the narrow band where temperatures are just right for liquid water. These worlds orbit the dead, but they themselves are not dead. They are survivors, echoes, quiet proof that even in the aftermath of stellar death, the story of planets may go on. Others may have formed from the remains of destroyed worlds. In the chaos of a young solar system, collisions are common. Planets can be shattered, moons torn apart, and debris scattered across the dark. Sometimes from this wreckage, new worlds slowly form, built from the remnants of earlier ones. We have seen hints of this in the dusty disks around some stars, where ring-shaped gaps suggest collisions or ongoing construction. Some exoplanets may be the cores of once larger planets, stripped bare of their outer layers. Others might be aggregates, assembled from fragments fused together by gravity and time. These are recycled worlds, not born whole, but rebuilt from the pieces of something else. Their surfaces may be rough, scarred, or molten. Their orbits may be tilted or eccentric, but they exist, and they remind us, in the softest way, that destruction is not always the end. Sometimes it is only the beginning of something new, stranger, rougher, and more resilient than what came before. There are planets that may have once belonged to another star system altogether. Planets form around stars, that much we know. But over the long, patient life of a galaxy, stars and their planets do not always stay together. Gravitational encounters, close flybys, or the chaotic dynamics of stellar clusters can fling planets from one star system into another. Some exoplanets may have begun their lives orbiting one star and ended up captured by a different one entirely. These interstellar adoptees can settle into strange orbits, tilted, elliptical, or unstable. We cannot always trace their true origin, but in some cases, their chemical signatures or their motions whisper that they do not quite belong. They are cosmic immigrants, pulled from one family into another, survivors of stellar drift and gravitational chance. And they remind us that solar systems are not sealed. They evolve, they trade parts, and sometimes they gather strangers from the stars. And yet, perhaps the most tender thought of all is still ahead, because some exoplanets may look very much like a younger version of what our own Earth once was. When we gaze at distant planets, we are not only seeing other worlds. Sometimes, we are seeing different versions of our own past. Some exoplanets may resemble early Earth, billions of years ago, when the atmosphere was thick with carbon dioxide or methane, and life, if it existed at all, was only just beginning to take hold. These young planets may still be forming continents, building atmospheres, or undergoing enormous geological change. Volcanic activity, delicate chemical reactions, and extreme weather could shape their futures, just as they once shaped ours. Studying them may help us understand how Earth came to be the way it is. What did our skies look like a full billion years ago? What gases filled the air? What storms raged over silent, sleeping oceans? Some exoplanets may hold the answer, snapshots of an earlier chapter in the long story of habitability, distant, silent echoes of the Earth before we were here to name it. We have also seen giant planets orbiting tiny, dim stars. Not all stars are big and bright. In fact, most stars in our galaxy are red dwarfs, small, faint, and remarkably long-lived. And around some of these quiet stars, we have found enormous planets. It seems unlikely at first. How could such a tiny star host a giant world? But nature, as always, finds a way. In several cases, we have detected Jupiter-sized planets orbiting stars that are barely a tenth the size of our Sun. These massive planets often lie very close to their stars, completing entire orbits in just a few days. The contrast is striking, a hulking planet looming beside a dim, ember-like star. These pairings gently unravel our earliest assumptions about how planets are born, and they hint that even modest stars can cradle large, dramatic systems. Let it be a soft reminder, as you rest, that size is not destiny, that in the quiet corners of the galaxy, strange and beautiful arrangements can still take shape. Now let your thoughts drift toward another wonder. Some stars carry planetary families of astonishing size. Our own solar system holds 8 planets, a comfortable number, familiar and steady. Yet other stars may cradle many more. Thanks to missions like Kepler and TESS, we have uncovered compact planetary systems with 5, 6, even 7 confirmed worlds, and hints of still more waiting quietly to be found. These systems are often tightly gathered, with planets circling far closer to their star than Mercury does to our Sun. In some cases, you could stand upon one world and watch another rise as a bright disk in the sky. Not a star, not a moon, a neighboring planet, near enough to shine like a lantern in the dark. Their orbits are often finely tuned, moving in resonance with one another, turning like the gears of a slow cosmic machine. Such systems softly challenge our sense of scale. They whisper that planets can gather and endure in patterns very different from our own, and they hint at something deeper still, that the architecture of a planetary system may be as varied as the stars themselves. But the strangest arrangements are still ahead, so let your breath settle and let us drift on. Other systems seem to hold only a single lonely planet. At the far edge of this spectrum, we find stars with just one known world, a solitary traveler circling in silence, with no companions in sight. We do not yet know whether these planets were born alone, or whether their siblings were flung away, shattered, or simply too small to reveal themselves to us. Yet the outcome remains the same, a single planet tracing its orbit in stillness, untouched by the pull of nearby kin. These lonely worlds may carry very steady histories, or very turbulent ones, depending on how they came to be. Some may be great gas giants moving in wide, slow arcs. Others may be small, rocky planets held close against the warmth of their stars. The skies of such a world might feel vast and quietly empty. No neighboring planets rising like moons. No gravitational harmonies shaping the turn of the seasons. Only one world and one sun drifting through the dark. It is a soft kind of beauty, a solitary rhythm within the vastness. Friends, a small request before we continue. Support Cosmic Lullaby with a like. It gently helps the channel grow and lets these journeys reach more sleepy travelers like you. Now, let us drift onward. Some exoplanets appear to be wrapped in thick, endless steam. Picture, if you will, a planet whose surface is lost beneath heavy veils of vapor. Not clouds like those of Earth, but dense, swirling layers of scalding mist. Some exoplanets may carry atmospheres made almost entirely of water vapor, born of intense heat that lifts whole oceans into the sky. These steam worlds most likely orbit close to their stars, where temperatures soar and water cannot linger as a liquid on the surface. What remains is a planet folded in fog, hidden beneath its own cloud tops. From space they might appear featureless, glowing faintly through the haze. Within, however, could lie a slow chaos of pressure, heat, and quiet chemistry. Some may still hold liquid water far below, or even a rocky surface deep beneath the mist. These are worlds in transition, where atmosphere and ocean blur into one another, and the boundary between sky and surface dissolves into vapor. There are also planets where ice may behave as though it were stone. Here on Earth, ice feels fragile. It melts in your hand. It cracks under pressure. Yet on some exoplanets, especially those far from their stars or hidden deep within thick atmospheres, ice can become something else entirely. Under crushing pressure and steady cold, water can crystallize into exotic forms, dense, heavy, and as solid as rock. These high-pressure ices, known as Ice 7 or Ice 10, do not melt easily. They may rest beneath deep oceans or lie buried within icy super-Earths, forming hard layers that behave more like stone than frozen water. On such worlds, glaciers may creep along under their own weight or stand motionless for eons. Mountains might rise, carved from ice that never softens. The boundary between water and geology quietly disappears, and beneath those solid crusts of crystalline ice, liquid oceans may still turn and stir, warmed by inner heat, hidden below miles of frozen pressure. Some worlds may be draped in exotic ices of ammonia or methane. Not all ice is made of water. On cold exoplanets, especially those far out in the outer regions of their systems, temperatures fall low enough for other substances to freeze. Ammonia, methane, nitrogen, gases that are invisible and harmless in the air we breathe, can settle into ices that coat a planet in pale blue, soft pink, or gentle yellow frost. These strange ices may form smooth plains, jagged ridges, or fields that glitter softly beneath a distant, dim sun. Some may slowly sublimate into thin, drifting atmospheres. Others may remain steady for billions of years. Such planets could resemble Pluto or the moons of Neptune, but on a far grander scale. Vast, frozen worlds, where chemistry itself becomes the sculptor of the land. The air may be faint and strange, the light dim and far away. Yet in their stillness, these icy planets are among the oldest and most enduring travelers within the galaxy. We have also found planets within the star clusters, in the very places where stars themselves are born. Most stars come into being within clusters, crowded stellar nurseries where hundreds, even thousands of suns ignite together inside great clouds of gas. For a long time we were uncertain whether planets could take shape in such restless surroundings. The gravity, the radiation, and the constant near encounters with other stars seemed as though they might make it impossible. And yet, we have now discovered planets even here, in these bright and crowded halls of starbirth. These exoplanets may circle their stars while nearby suns blaze fiercely with ultraviolet light. They may form quickly or struggle to keep hold of their atmospheres. Some may be cast away early, becoming rogue planets adrift in the dark. Others manage to remain. Their skies would be filled with stars, brighter and more numerous than anything we glimpse from Earth. It is a more dangerous cradle, yet planets, and perhaps even life, seem to find their way, even within the glowing, restless halls where the stars themselves are only just beginning to shine. And there is still more to come, for some exoplanets have formed in settings we once thought impossible. When scientists first began discovering worlds beyond our own, they expected them to resemble the familiar shape of our solar system: rocky inner worlds, gas giants farther out, gentle orbits, quiet stars. Yet what we have discovered instead is far stranger. Some exoplanets formed within binary or trinary star systems. Some orbit pulsars, the rapidly spinning remnants of exploded stars. Others took shape in metal-poor environments where planet formation was long thought unlikely. In every case, nature has proved more inventive than theory. Planet formation, it turns out, is not fragile. It is opportunistic. Wherever there is material, gravity gets to work, pulling, clumping, colliding, shaping, even in the aftermath of cosmic violence. Even on the sparse outskirts of a system, even around stars that seemed too unstable, too faint, or too crowded, planets appear. They do not need perfect conditions. Only time, dust, and the quiet patience of gravity. Let your breath slow for a moment and consider this. Somewhere out there, a world is forming right now, and the strangest examples are still ahead. We have detected planets around stars only a few million years old. Stars live for billions of years, yet some planets begin forming almost immediately after their stars ignite. In several cases, we have found worlds orbiting stars only a few million years old, cosmic infants, still wrapped in the remains of their birth clouds. These stars are young, volatile, and often surrounded by disks of gas and dust. Within those disks, planets begin to grow. Dust grains stick together, clumps become rocks, rocks become worlds. Some of these newborn planets are still glowing with leftover heat. Others may be pulling in material, growing larger by the day. Their orbits may still be shifting. Their atmospheres may not yet be stable, and yet they are real. Worlds in progress, still taking shape beneath the light of a very young sun. They remind us that planet formation is not merely a theory. It is something we can watch right now, in real time. Some planetary systems are older than the Earth itself. Our own Earth formed about 4.5 billion years ago. But we have discovered exoplanetary systems that are far older, as old as 10 or even 11 billion years. These planets have been orbiting their stars since long before our sun was born. They have survived galactic mergers, stellar outbursts, and billions of orbits without being destroyed. One such system, Kepler-44, hosts 5 small rocky planets. The star is more than twice as old as the sun, and yet its planets are still there, circling steadily. These ancient systems reveal that planets formed early in the history of the universe, even when heavy elements were rare. They are time capsules, leftovers from the early universe, holding clues about what the first planetary systems might have looked like. If life had time to arise there, it could be unimaginably old. We may be newcomers in a galaxy already filled with ancient, quiet worlds. Let your thoughts drift on that thought a while, because the sky above you is older and stranger than any dream. There are planets with masses measured in tens of Jupiters. Some exoplanets are enormous, so massive they stretch the very definition of what a planet even is. These giants are often 10, 15, or even 20 times the mass of Jupiter. They blur the line between planet and brown dwarf, objects too small to ignite into stars, yet too large to be typical planets. These supermassive worlds often orbit far from their stars, glowing faintly with retained heat. Some may have dense cores. Others might be almost entirely made of hydrogen and helium, with atmospheres thousands of kilometers thick. Their gravity would be immense. Their weather systems could span entire hemispheres, and any moon orbiting them might itself be large enough to support life. These are the heavyweights of the planetary family. Strange, slow-burning giants that challenge our sense of scale and possibility. Not failed stars, not oversized planets, but something unique and quietly colossal. Some worlds might be dense enough to crush iron. Planets come in all sizes and all densities. Some are so light they would float on water. Others are so compact that their interiors are pressed together with unimaginable force. We have found rocky exoplanets that may be twice as dense as Earth, or even more. Their surfaces might seem familiar, solid, cratered, perhaps mountainous, but beneath, the pressure climbs rapidly. In some cases, it could be enough to compress iron into new, exotic forms. These planets may possess huge metallic cores, stronger gravity, and shorter planetary radii despite their great mass. They are small and yet heavy, the compact remnants of larger systems or the result of unique formation histories. Walking on one would feel strange. The pull beneath your feet would be stronger, heavier, unfamiliar. These worlds are gentle reminders that not all planets are soft, gentle spheres. Some are tightly wound, compressed by gravity into iron-rich mysteries waiting in the dark. And still, the sky holds an even softer surprise. We have found planets so lightweight they could float on water. In contrast to those dense, iron-heavy worlds, some exoplanets are remarkably fluffy. These are low-density gas giants, planets with vast diameters but very little mass. One familiar example is Saturn, which is the least dense planet in our own solar system. Yet some exoplanets go even further. With densities lower than wood, they are made almost entirely of gas. And if you could find an ocean large enough, they would float upon it. These puffy planets often orbit close to their stars, where the heat causes their atmospheres to swell dramatically. They may have small, dense cores hidden beneath vast, transparent skies. Their clouds might be thin and high, their winds slow and drifting. They are enormous yet fragile worlds, seeming more like bubbles than spheres, delicate giants drifting in the warmth of their stars, held together by the gentlest pull of gravity and gas. Some planets may have lost their atmospheres long ago. A planet's atmosphere is a fragile thing, and over time it can be stripped away, blown into space by solar wind, radiation, or ancient impacts. Some exoplanets, especially small rocky ones near their stars, may once have possessed thick atmospheres, only to lose them billions of years ago. We have glimpsed signs of this in the spectral fingerprints of certain worlds, where little or no atmospheric absorption is detected. The causes can vary, and the strangest examples, as always, are still ahead in our slow journey through the dark. A weak magnetic field can leave a planet unshielded. A violent stellar youth may blast the air away, or slow, patient erosion across eons can thin the skies to nothing at all. What remains is a bare, airless world, exposed stone, lifeless plains, and perhaps the faint fossil imprint of what once was. These are planetary ghosts, stripped down to their cores, drifting in silence. Let this thought settle softly as you breathe. They remind us that even planets can be weathered by time itself. Others, far from fading, are still actively gaining mass from their disks. Planet formation does not end in an instant. Around young stars, swirling disks of gas and dust can linger for millions of years. And in that long window, planets continue to grow. Some are still gathering material from these protoplanetary disks, pulling in gas, dust, and rock as they orbit. We have seen direct evidence of this, catching glimpses of planets in progress, glowing in infrared light, still warm from their birth, spiral patterns in the disk, gaps carved out by gravity, and bright clumps of matter, all whisper of ongoing creation. These infant worlds may still be hot and unstable, their surfaces unfinished, their atmospheres thick and turbulent. We are watching them in the very act of becoming, not finished worlds, but places still shaping their identity. It is a rare and beautiful thing to witness the birth of a planet, and to know that within the quiet swirl of dust and light, something new is taking shape. Let your thoughts wander through that soft glow for a moment, and consider what strangeness might be waiting still ahead in this journey. We have also witnessed the destruction of a planet in real time. Planets are often thought of as permanent, but in certain cases we have seen them vanish. One candidate observed by the Kepler Space Telescope appeared to dim and flicker in a way that suggested it was shedding mass, leaving behind a dusty tail as it orbited its star. The planet, likely small and rocky, was being roasted by intense heat and slowly worn away. Its material vaporized and carried off into the dark. In another system, astronomers spotted what may have been a planet colliding with something large, perhaps another planet, producing a sudden bright flare of infrared light. These are not just theories, they are events we have observed, the final chapters of a planet's story playing out before us. Some planets are born before our eyes, others vanish before we can begin to understand them. Creation and destruction, side by side, in the quiet machinery of the cosmos. Some exoplanets may be covered in metallic snow. On Earth, snow is made of ice, soft, light, and familiar. But in the atmospheres of certain exoplanets, especially hot gas giants, snow may be made of something far stranger. Metals such as titanium and iron can exist as vapor high in the sky, condensing into droplets as they cool. Under the right conditions, those droplets could solidify and fall, forming clouds and even snow made of metal. The snowflakes would look nothing like Earth's, more like tiny shards or crystals, heavy and glittering as they drift. On some worlds, aluminum oxide could form high-altitude clouds, giving rise to snowfall made of the same minerals found in sapphires. This metallic snow may never actually reach the surface, vaporizing on its long descent. Yet above, in those high skies, it drifts quietly, a shimmer of falling metal beneath alien suns. Strange weather shaped not by water, but by heat, pressure, and elements we usually find locked inside stone. There are also planets trapped in tight gravitational dances. Some planetary systems feel more like choreography than chaos. We have discovered exoplanets caught in precise interlocking orbits, gravitational dances in which each planet moves in rhythm with its neighbors. These are called mean motion resonances. One planet might complete exactly 2 orbits for every 3 of another. These patterns are not random. They are the result of long, patient interactions, where gravity gently nudges each planet into a stable, repeating path. Such arrangements can prevent collisions, steady orbits, and allow many planets to exist close together. In systems like TRAPPIST-1, where 7 rocky planets circle a small star, we can see this harmony in action. It is as if the planets are keeping time, moving through space with a shared rhythm, a quiet cosmic clockwork. These dances may last for billions of years, their patterns preserved long after we are gone, their balance held in the stillness between the stars. Some systems, however, appear unstable and may collapse in the future. Not every planetary family is harmonious. A few seem precariously arranged, with orbits that tug, stretch, or tilt across time. Such systems may look stable now, yet gravitational simulations suggest they could unravel in 10 million years, 100 million, or even more. Planets might be flung out, orbits might shift. Some may spiral into their stars. Others could crash into one another, triggering cataclysmic collisions. These are unstable systems, where planets teeter on the edge of balance. Often they were shaped by chaotic events, migrating giants, close encounters, or ancient disruptions. What we observe now may be only a snapshot of a system in slow collapse, like a spinning top that is not yet tipped. Even the universe has its fragile arrangements, places where gravity's delicate work may one day come undone, and the planets, for all their size and silence, are not immune to falling. Let that thought drift by as gently as your breath, because the strangest orbits are still ahead. We have found planets with extremely tilted orbits. Most planets travel near the same plane, like flat disks spinning around their star. But some exoplanets refuse that pattern. Their orbits are tilted, sometimes steeply, sometimes wildly off-axis. In the most extreme cases, they orbit at sharp angles to their star's equator, or even perpendicular to it. These tilted paths may be caused by gravitational interactions with other planets, with nearby stars, or with ancient collisions long ago. Some worlds were probably born in the usual way, then knocked off course by later events. Such tilted orbits can shape seasons, climate, and stability in strange ways. They also hint at dramatic pasts, histories of motion and disruption, where gravity rewrote the script. From afar, we see only the current path, but the tilt itself is a clue. A gentle tilt that whispers a planet's story is never simple. It has turned, it has shifted, and now it moves in quiet defiance of the ordinary. Let your thoughts drift, for some planets spin backward compared to their orbits. Worlds do not merely circle their stars, they also spin, and for most of them, that spin follows the same direction as their journey around the star. But some exoplanets do the opposite. They orbit one way and rotate the other. This is called retrograde rotation, and it is likely the result of dramatic events, collisions with other planets, tidal interactions, or powerful gravitational encounters that flip the axis. We have even glimpsed planets in retrograde orbits, circling their star in the opposite direction of its own spin. These backward worlds are rare, yet real. Their days run in reverse. Their weather systems turn in unfamiliar patterns. Sunrises and sunsets arrive in the opposite order. If you stood on one, the sky itself might feel subtly wrong, the rhythms of light and time drifting against the flow. These planets refuse the rules. They are the quiet rebels of the galaxy, slowly turning against the current of their stars. Now let your breath slow and imagine that we have measured the winds sweeping across entire alien worlds. Even without seeing them directly, we can sense the winds of exoplanets, and they are swift, in some cases extraordinarily swift. Using precise spectroscopic techniques, astronomers have detected winds on gas giants moving at more than 800 kilometers an hour, fast enough to cross a continent in under an hour. These winds are often driven by the immense temperature differences between a planet's dayside and nightside, especially for tidally locked planets where one hemisphere forever faces the star. The heat builds pressure gradients, and the atmosphere flows, rushing around the globe in an enormous jet stream. Some planets carry equatorial winds that ferry heat from the dayside to the nightside. Others may host storms that circle the world without end. We cannot feel these winds. We cannot hear them. Yet in the way starlight shifts and flickers, we glimpse their motion, a soft whisper of weather from a world far away. And there is more still to wander through before you rest. Some exoplanets are battered by intense stellar flares. Not every star is gentle. Some, especially young red dwarfs, release powerful flares, sudden bursts of radiation that can be thousands of times stronger than anything our own sun produces. Planets orbiting close to these stars can be caught inside the storm. Such exoplanets may be pounded again and again, their atmospheres scoured by ultraviolet and X-ray radiation. If they have magnetic fields, they may find shelter. If they do not, they risk losing their air, stripped away molecule by molecule. We have watched stars like Proxima Centauri flare with sudden fury and wondered what it might mean for the planets nearby. Could life endure such violent energy? Could an atmosphere ever recover, or would the surface be forever scarred by the light of a sun too young and too wild? These flare-battered worlds remind us that habitability is not only about distance, it is also about stability and the temperament of the star you call home. Others rest in the calm glow of quiet red dwarfs. Not all red dwarfs are restless. Some are remarkably steady, slow-burning stars that shed gentle light for trillions of years. Around such stars, planets can orbit close enough to receive constant warmth without being scoured by flares. These calm red dwarfs are among the most promising places to look for life. Their habitable zones are small but stable. A planet within that zone might be tidally locked, one side in endless day, the other in endless night. Yet the climate could still be mild, especially along the twilight ring stretched between light and dark. Life, if it arose there, might have billions of years to evolve undisturbed. These stars do not rush. They live long, quiet lives, and the worlds they cradle may be among the oldest, most enduring, and most gently lit places in the galaxy, slowly turning beneath a peaceful, ruby-colored sun. Let your thoughts wander a little further, for some planets may be wrapped in auroras that never end. Auroras, those glowing curtains of light near the poles of Earth, are born when charged particles meet our magnetic field. But on some exoplanets, auroras could be far more powerful and far more enduring. Especially for planets orbiting close to active stars and carrying strong magnetic fields of their own, auroras may spread across entire hemispheres or wrap the world in continuous bands of color. These lights could shimmer not only at the poles, but around the equator, a glowing electric dance woven across the sky. If the planet is tidally locked, its day side might blaze with starlight, while the night side glows with auroral fire. And on gas giants with vast magnetic fields, the auroras may be visible from space, green, blue, or violet arcs shimmering across the clouds. These are not silent skies. They are alive with light, shaped not just by air, but by the stars themselves. We have also caught hints of clouds made of vaporized rock. On some of the hottest exoplanets, the atmosphere is so extreme that stone itself can vaporize, rising rising as gas, condensing into clouds, and drifting down again as particles suspended in the air. These mineral clouds may hold silicates, aluminum oxide, or other compounds usually locked inside solid rock. Through spectroscopy, we have glimpsed these strange clouds absorbing and scattering light in patterns unlike anything on Earth. They could form shimmering hazes, metallic storms, or skies tinted yellow, gray, or even deep blood red. On some worlds, the upper atmosphere may be filled with sand-like dust carried on supersonic winds. These clouds are neither soft nor familiar. They are the product of heat and gravity, forging strange weather from solid matter. It is hard to imagine, and yet it is real. On such worlds, the sky is not made of water. It is made of rock, ground down to mist, drifting high above the surface. And still ahead, softer and stranger, there are worlds that may be slowly falling into their stars. Orbits are not always eternal. For some exoplanets, especially those drifting very close to their stars, gravitational interactions and tidal forces can nudge them slowly inward over time. Quietly, patiently, these planets lose altitude. Their orbits shrink bit by bit, year by year, in a descent so gentle it seems almost like a lullaby. Eventually, they may fall into their stars, consumed in a final soft flare of light and heat. And astronomers have already noticed hints of this fate. Certain planets show orbital periods that shorten by fractions of a second across long stretches of observation. The end may lie millions of years away, or only thousands, but it is written into their motion. Some worlds, once stable, are now destined to vanish, swallowed by the very stars that once cradled them in warmth. These are planets in slow descent. Their skies may still be bright, their days may still pass in familiar rhythm. Yet above them, gravity is pulling, and somewhere in the silence, a clock is quietly ticking. Others take the opposite path. Instead of falling inward, they are cast outward, flung from their systems entirely. This can happen in the early days of a planetary system, when giant planets tug on one another with heavy gravitational hands. A close encounter can give a planet just enough velocity to break free of its star's hold, becoming a rogue, a lonely wanderer drifting through interstellar space. These rogue planets are difficult to find. They emit no light of their own, and they orbit nothing at all. But with powerful infrared telescopes, a handful have already been glimpsed. Some may be the size of Jupiter, others could be Earth-like, but frozen solid down to their bones. Without a star, they are cold, dark, and profoundly alone. And yet, some may still hold warmth deep inside. A few might even shelter subsurface oceans, kept liquid by the slow decay of radioactive elements in their cores. These are the ultimate wanderers, cast out, unbound, but still planets in every meaningful sense, worlds adrift, carrying secrets we may never hear. There are also exoplanets whose orbits stretch across entire systems. Most planets circle fairly close to their stars, at distances where light, warmth, and gravity settle into a delicate balance. But some exoplanets trace paths that reach across vast expanses, looping through their systems on long, unhurried journeys. These wide-orbit planets may take hundreds or even thousands of years to complete a single lap around their star. Some lie so far out that they are only barely bound by gravity at all. Others follow elliptical paths, swinging in close before sailing back into the deep dark. Such extended trajectories may have been shaped by planetary migration or by violent encounters somewhere in the past. Astronomers have even spotted possible planets orbiting hundreds of astronomical units from their stars, so far away that their suns appear as little more than bright specks in the sky. These worlds drift on the outer edge of their systems, nearly free, tracing orbits as wide and slow as time itself. And then there are the planets that sit in a kind of cosmic Goldilocks zone, not too hot, not too cold. Somewhere between the fierce furnace of a star and the frozen edges of space lies a narrow, precious region. the habitable zone. Here, temperatures are just right for liquid water to linger on a planet's surface. Not too hot, not too cold, but just right. Earth belongs to this zone, and so does a growing family of exoplanets. They orbit at the perfect distance for water to remain stable, one of the key ingredients for life as we understand it. Yet sitting in this gentle band is not, by itself, a promise of habitability. A planet's atmosphere, its rotation, its surface conditions, all quietly shape whether life could ever take root. Still, it is a beautiful place to begin looking. These planets are among our finest candidates for life. Whether they are rocky, wrapped in oceans, or draped in soft clouds, they rest in the very same sweet spot we call home, bathed in gentle starlight, balanced on the edge of possibility. And here is a thought to carry gently forward. Some exoplanets do more than simply linger in the habitable zone. Their surface temperatures appear remarkably close to Earth's. These temperate worlds are especially intriguing. They orbit quietly, receiving just enough starlight to keep them from freezing or boiling. Their estimated equilibrium temperatures hint at the possibility of water, moderate climates, and perhaps even weather patterns that would feel almost familiar. Planets such as Kepler 442b and TOI 700d are among these gentle, promising worlds. We do not yet know whether they are truly Earth-like. Their atmospheres, if they possess any, remain a soft mystery. But temperature is a meaningful clue, a whispered hint that these planets might not feel entirely alien. They might have calm skies, winds that drift across quiet oceans, or clouds that gather in the softness of evening light. They might be warm enough for rain, and still enough for life to slowly grow. We cannot see them up close, but we can imagine standing there beneath a familiar foreign sky. Some exoplanets, though, could carry weather patterns unlike anything we have ever known. Weather is a reflection of a planet's chemistry, its temperature, its atmosphere. And when those ingredients change, so does everything we once thought we understood. On some exoplanets, the weather may be entirely alien. There might be clouds made of molten metal and rain composed of molten glass or liquid methane. Winds could race at tens of thousands of kilometers per hour, sweeping across landscapes that have never known stillness. On colder planets, it might snow ammonia in slow, silent drifts. On hotter ones, the air might shimmer with silica dust. The colors of the sky could be red or yellow, or a black so deep it seems to swallow the horizon. Lightning might flash through clouds of vaporized rock. Storms could last for centuries. Some planets might have permanent jet streams that never shift their course. Others may endure sudden planet-wide weather events, triggered by flares from their star. These are not Earth-like climates. They are weather systems built from unfamiliar physics, beautiful, terrifying, and quietly unimaginable. And still, not all geological activity has to be fiery. On some exoplanets, especially the cold, icy ones, volcanoes may erupt not with molten rock, but with slushy mixtures of water, ammonia, or methane. These cryovolcanoes are already known from moons in our own solar system, like Enceladus and Triton, and it is very likely they exist on distant exoplanets too, quietly reshaping frozen worlds beneath a sky full of stars. Instead of molten lava, these worlds exhale cold liquids into their thin skies, mists that freeze in midair and drift back down as a slow, glittering snow. Beneath the surface, hidden oceans may still hold their warmth, kept alive by the quiet heat of the planet's own heart, sealed away beneath thick layers of ice for billions of years. In those buried seas, chemistry could grow patient and complex, and somewhere in that darkness, perhaps even life could stir. The surface may look frozen and motionless, but far below, the world is alive with a soft, unseen motion. Cracks open, water rises, ice flows like stone. In the silence of the deep, something moves. A hidden ocean, dreaming beneath a frozen world. Let your breath slow now, as we drift toward the quietest corners of the galaxy. The Milky Way is a place of endless motion. Stars circle its center, clouds of gas fold themselves into new suns, and planets spin through the dark. Yet some regions are calmer than others. Out along the far edges of the galaxy, beyond the crowded core and the bright spiral arms, stars and their planets glide more slowly, in deeper solitude. These are the galactic suburbs, dim and still and very old. Some exoplanets circle stars in these peaceful zones, where radiation is low and close encounters between stars are rare. Their orbits can remain steady for billions of years. No nearby star arrives to shake them. No sudden tide bends their path. There is only a gentle, endless turning under the faint light of distant suns. If life ever wakes in such a place, it would have time to evolve, to adapt, to endure. These worlds may be cold and far away, yet in their silence there is a kind of cosmic shelter, a stillness in which something lasting could quietly begin. Others race through wilder skies, through crowded, chaotic starfields. Not every planetary system rests in peace. Some are born in the dense heart of the galaxy, near the bulge, along the spiral arms, or inside globular clusters packed tight with stars. In those regions, suns pass close to one another again and again. Gravity tugs, orbits shift, and planets can be flung onto strange new paths, or even carried away by a passing star. A world drifting through such a crowded starfield might look up and see dozens of suns, bright and close, and always in motion. Its night sky could glow with constant light. But beauty here comes with risk. A gentle gravitational nudge from a neighboring star could unbalance an orbit. Radiation from a nearby supernova could strip an atmosphere clean. These planets live along the edge of chaos, rushing through busy space, escaping disaster with every turn. And yet they endure, holding their orbits, circling their stars like dancers in a crowded, ever-shifting ballroom of fire and light. And there are stranger companions still. We have discovered planets orbiting pulsars, the dead stars that pulse with light. Pulsars are what remain after massive stars end their lives in a supernova. Dense, rapidly spinning neutron stars that sweep the darkness with narrow beams, like lighthouses turning across an empty sea. For a long time, no one believed planets could survive such violent endings, but astonishingly, some do. In fact, the very first confirmed exoplanets ever found circled a pulsar, PSR B1257+12. These worlds orbit a star long dead, one that spins dozens of times each second and pulses steadily into the void. Their origin is still debated. They may be survivors of the original planetary family, or they may have formed later, drawn together from the fallback material that swirled around the pulsar after its death, gathering slowly into new worlds. Either way, they are among the strangest planets we know, silent companions to a collapsed core, circling a star that no longer shines with fusion, yet still pulses with the afterglow of its own ending. Planets around the dead, ghost worlds orbiting ghosts. Some planets may have lived through the explosions of nearby stars. Supernovae are among the most powerful events in the universe. Brilliant, violent stellar deaths that can, for a brief moment, outshine entire galaxies. When one erupts, it can erase everything close to it, and yet some exoplanets may have endured those cosmic blasts. If a star in a binary pair explodes, the surviving companion and its worlds might remain, scorched, but still turning in their orbits. In other cases, a planet may have taken shape later, born from the drifting debris. Astronomers have found heavy elements such as iron and calcium in the atmospheres of certain white dwarfs, a quiet sign that planets once circled them, and perhaps still do. Any world that lingered after such a blast would carry the imprint of catastrophe. Its surface might be seared, its air changed forever, and still it would exist, a planet that lived through a star's final breath, a witness to cosmic death and to cosmic survival. well. Now let your thoughts wander a little further, toward worlds whose skies are filled with stranger air. There are planets with atmospheres rich in exotic gases. Earth's own air feels familiar, mostly nitrogen with a soft touch of oxygen, a little water vapor, some carbon dioxide. But the atmospheres of exoplanets can be far stranger than this. Some are heavy with hydrogen and helium, like the great gas giants. Others carry methane, carbon monoxide, or thick clouds built from sulfur compounds. One exoplanet, HD 209,458b, shows clear signs of hydrogen escaping into space, its atmosphere puffed outward and slowly drifting away. Another reveals faint traces of titanium oxide high in its skies. These gases shape everything: temperature, color, weather, even the kind of light the planet gives back to the stars. Some atmospheres may be hot and transparent, others may be murky and choking, and some may look clear from a distance, yet hide layered chemistry below. With every new discovery, our sense of what an atmosphere can be gently expands. Air, it turns out, is not always breathable, not always blue, not always soft. Sometimes it is metal, sometimes it burns. And still, there is more to imagine before the night ends. Some planets may be rich in carbon or poor in oxygen. Here on Earth, oxygen shapes our biology. But in other corners of the galaxy, carbon may reign instead. Some exoplanets may have formed in regions where carbon outnumbered oxygen, giving rise to chemistry we have only begun to understand. These so-called carbon planets could hold graphite or diamond in abundance, with mountains of pure carbon, or dark oceans of hydrocarbons resting beneath cloudy skies. Their air might carry methane instead of water vapor. Their soils might glitter with unfamiliar minerals. And elsewhere, other worlds may be poor in oxygen, wrapped in iron-rich surfaces and carbon-laced clouds. Life, if it ever awakens on such a world, would be very different from our own. The rules would change. The elements would tell different stories, softly, patiently, in the long quiet of the cosmos. These distant worlds gently challenge every assumption we carry with us. Not every planet, it turns out, will resemble Earth. Some are forged from different ratios of elements, shaped by different conditions, built upon entirely different foundations. And yet, they too are real places, where an alien chemistry quietly writes its own version of what it means to be a world. Let your breath slow for a moment, and consider this. We have only just begun to search for what scientists call biosignatures on those distant worlds. A biosignature is a clue, a subtle hint that life might be present, even from many light years away. Here on Earth, our atmosphere contains oxygen, methane, and water vapor woven together in patterns that are difficult to explain without the presence of biology. And now, astronomers are beginning to look for similar patterns on the exoplanets scattered across the galaxy. Using advanced telescopes, we can split distant starlight into spectra, searching within it for the delicate fingerprints of life-related molecules. It is patient, delicate work. Clouds, temperatures, and the type of star all shape the results. And yet, already, there are intriguing candidates whispering back to us. Some planets show gentle signs of water vapor. Others carry suspicious amounts of carbon compounds drifting through their skies. In the years ahead, new missions will search even deeper, listening for ozone, for chlorophyll-like signatures, for chemical imbalances that suggest something living might be at work. We have not yet found life, not yet. But we are listening more carefully than ever before, watching for the tiniest flicker of biology in the great silence between the stars. And the strangest discoveries may still be ahead of us. Some exoplanets, you may find, could be wrapped in dust storms that last for years without end. Here on Earth, dust storms are temporary, brief, sweeping visitors that come and go with the seasons. But on some exoplanets, especially those with dry atmospheres and thin, wispy clouds, the dust storms may never fully settle. Winds move across barren landscapes, lifting fine particles into the air, swirling them endlessly through the sky. Some of these worlds may be so dry and so hot that global dust storms last for years, or even longer than that. The skies would turn a soft copper or a deep, drifting brown. The sun would fade behind slow, wandering haze. Seen from space, the planet might look smooth and soft, its features buried beneath ever-moving clouds of fine grit. These storms shape temperature, light, and even the chemistry of the atmosphere itself. They may shape the planet's climate entirely. And if any life ever existed there, it would have had to adapt, not to rain or snow, but to an endless hush of dust, stirred by a slow, relentless wind. Others, by contrast, might reflect so much light that they shine like beacons in the dark. Some planets are almost invisible, dark and muted, difficult to detect, but others are brilliant. Certain exoplanets reflect huge amounts of starlight, either because of high reflective clouds or smooth surfaces coated in ice or vapor. A planet like Kepler 7b, for instance, may be covered in silicate clouds that gleam like polished stone. Others may carry vast reflective layers of metal oxides or exotic compounds we have barely begun to understand. These worlds act like mirrors, glowing with borrowed light, visible even from hundreds of light years away. Their albedos, the measure of how much light they reflect, are among the highest we have ever seen. In some cases, these planets outshine their own stars at certain wavelengths. They do not make their own light, they simply echo it. Brighter than Venus, brighter than snow. These planets do not hide in the darkness. They shimmer, they glow. And they remind us, softly, that sometimes it is reflection, not heat, that makes a world luminous. Let your thoughts wander now to something familiar. Some planetary systems out there resemble scaled-up versions of our own. Not every exoplanet system is chaotic or strange. Some, surprisingly, look a great deal like home, only larger. We have found systems where smaller rocky planets orbit closer to the star, while larger gas giants sit farther out, like a stretched version of our own solar system. Some even include asteroid belts, or icy outer zones, much like our own Kuiper belt. These similarities suggest that certain laws of planetary formation may be universal. Gravity gently arranges the dust and gas. Rocky worlds take shape near the star, where it is warmer. Gases condense farther out, where the cold deepens. The results feel familiar, but written on a grander scale. Perhaps Earth is not so unique after all. Perhaps other solar systems follow a similar rhythm, echoing ours across the galaxy. We may not yet know if they hold moons, oceans, or life. But when we look at them, we see a structure we recognize, a quiet reminder that our place in the cosmos may not be as rare as we once believed. Others, however, follow rules we are only beginning to understand. Many planetary systems break every rule we thought we knew. Gas giants that orbit closer to their star than Mercury does to ours. Planets moving along tilted, elliptical, or even backwards orbits. Stars carrying more planets than we ever thought possible. Moons that may rival the size of planets, or planets that migrate slowly from their birthplaces, shifting the entire architecture of a system as they drift. These strange arrangements gently defy our expectations. They do not fit the tidy models of how planets should behave, and they invite us to rethink the very basics of what we know. Perhaps planet formation is less orderly than we once imagined. Perhaps it is wild, creative, endlessly flexible. Each new system we find adds another variation to the pattern. Each planet tells a new version of the same old story. The more we discover, the more layered the picture becomes, and the more we come to realize the universe is not following a script written long ago. It is improvising, quietly, patiently, building worlds we never thought to imagine. And the most delicate revelations, perhaps, are still waiting for us just ahead. We are now building telescopes to see these worlds directly. Until now, most exoplanets have been detected only indirectly, by the way they dim their star's light or gently shift it as they orbit. But now, we are entering a new era. Engineers and scientists are building powerful telescopes designed to see these worlds directly, not merely infer their presence, but actually photograph them. These instruments will use coronagraphs to block out the overwhelming glare of starlight, or vast star shades placed far out in space to create artificial eclipses. The goal is to glimpse an exoplanet as a small, faint dot beside the brilliance of its star. From that single dot, we can extract light, study its atmosphere, and even search for signs of life. Telescopes like the Nancy Grace Roman Space Telescope and future missions such as LUVOIR or Habitable Worlds Observatory aim to do what once seemed impossible, to take portraits of alien worlds. Soon, exoplanets will no longer be only shadows or faint signals in the data. They will be places seen with our own eyes. Some planets may already have been photographed in blurry detail. It has already begun. Using extreme precision and clever techniques, astronomers have directly imaged a handful of exoplanets, enormous gas giants drifting far from their stars. These images are not detailed. They do not show continents or clouds, only tiny specks of light, blurry and faint, but they are real. We have captured the glow of heat from a planet still cooling after its formation. We have watched distant gas giants orbit slowly across the years, confirming their steady motion through space. The first of these images, like those of the HR 8799 planetary system, mark a new chapter in astronomy. They are crude by modern standards, yet they are history, the first time humanity has ever seen light coming directly from a world orbiting another star. As our instruments improve, so too will the images. Someday we may see weather systems, oceans, or even signs of life. For now, we have a blur, a whisper, a beginning. And so the search for life often begins with exoplanets. When we imagine life beyond Earth, we think of planets, places with air, water, sunlight, and time. And so the search begins with these distant worlds. We look for those that lie within the habitable zone. We scan for oxygen, methane, and other chemical signatures of biology. We study their orbits, their stars, their long, slow paths through the dark. Every detection brings new questions. Could this planet hold water? Could it shelter microbes? Could anything at all live there? Even the smallest hint, a spectral wobble, a faint absorption line, sends ripples through the scientific world. Because if we ever find life, it will almost certainly be on a planet, not in a gas cloud or an asteroid belt, but on a distant world that quietly turned for billions of years, unnoticed. Exoplanets are our best hope, our mirrors, our windows, the places we search when we wonder not just whether life exists, but what other stories the universe might be telling. Every new discovery reminds us how strange the universe can be. The more exoplanets we find, the stranger the universe becomes. We expected Earth-like planets. What we found were lava worlds, rogue wanderers, planets with icy rings or molten skies. We found systems with dozens of tightly packed planets, planets that orbit dead stars, planets where weather, chemistry, and gravity dance together in ways we had never imagined. Each discovery adds a new twist, a new shape, a new possibility. The universe is not only vast, it is inventive, and the planets we have seen so far, just a few thousand, are likely only a tiny fraction of what truly exists. The surprises keep coming, and with each one, we remember that the cosmos is not simple, it is not familiar, but it is endlessly creative. And by exploring these distant worlds, we learn to widen our imagination and find wonder in the unexpected. unexpected. There may be more planets than stars in the Milky Way. For centuries, we imagined planets as rare, small companions circling stars here and there. But today, the evidence is overwhelming. Planets are everywhere. The average star in our galaxy likely hosts at least one planet, and many host several, which means there may be more planets in the Milky Way than there are stars. Hundreds of billions of worlds. Some are giant, some small, some scorching, some frozen. Many are unlike anything we have ever seen before. But the numbers point to something remarkable, that planetary systems are not rare exceptions. They are the norm. The galaxy is not simply a field of stars. It is a garden of worlds, each one following its own path, each one a quiet possibility. And somewhere among those billions, some may be blue, some may breathe, some may be waiting. Somewhere out there, a planet like Earth might be waiting. We do not know where. We do not know what it looks like, but the odds are with us. Among the countless stars and their countless planets, there are surely some like Earth, rocky, warm, wet, and alive. It might orbit a small red sun, or a bright yellow one. It might have oceans and forests, or forms of life we would never recognize. Perhaps it is quiet. Perhaps it is only just beginning. Or perhaps it is ancient, with civilizations that rose and fell while Earth was still molten. We have not found it yet, but we are looking. Every telescope, every mission, every exoplanet discovered brings us closer. And when we finally find that world, that small, distant twin, it will change everything. It will remind us that we are not alone in the quiet, vast dark, that other Earths exist, and that the universe is, after all, a place meant to be shared. And now our journey draws gently to a close. We have wandered far tonight, beyond the warmth of our sun, past the edge of familiar skies, and into a galaxy filled with silent planets. Each one a quiet answer to the question, what else might be out there? We have drifted through dust storms and burning skies, through oceans locked beneath ice, and through atmospheres made of metal, wind, or cloud. We have watched stars flare and fade, seen planets flung into the dark, and imagined life, strange, fragile, impossible, taking root on worlds we will never touch. And all along the way, one thought has remained. The universe is not only vast, but full of places. Places with gravity and weather, with histories and futures, with stories still unfolding in the quiet. Each exoplanet we visited tonight, whether real, theorized, or barely glimpsed, was a little world of its own, a small gravity well in a sea of starlight, a question wrapped in silence, waiting for us to notice. And perhaps that is the wonder of it, that even as you lie here still and safe, the cosmos is continuing. Stars are shining, planets are turning, and in some far-off sky, a world not unlike our own might be spinning slowly through its night. So if your eyes are growing heavy now, if your breath has settled into a soft rhythm, if your thoughts have begun to drift like stardust through the dark, you do not need to return. You are already part of this universe, already floating, already home. Thank you for sharing this moment, this quiet voyage among distant worlds. And if it helped you rest, you are always welcome to return, to listen again, to dream again, to keep wondering. And if you happen to still be awake, you can go ahead and watch the next video now. There are always more wonders waiting, more science, more stillness, more stars. But for now, rest. The planets will keep turning. The universe will wait. Good night.